At the last lesson, we have learned about transformations, and today we will learn more deeply into a particular type of transformation, which is translation. Okay, so I have a door like this, and vector endpoint A and B. And when the door slides from point A to point B, we have vector AB. Now let's to arbitrary point C and E on the door. And we will have vector point D and F on this door. So what is the relationship between vector CD and vector AB and vector EF and vector AB? Anyone know? Yeah, that's right. Vector AB equals to vector CD equals to vector EF. So we can conclude that the door is translated by vector AB. Okay. So now let's move to the definition. Let vector V be on the plane. The transformation that transforms each point M into M prime, such as vector M prime equals to vector V is called a translation by vector V. So here is the definition of translation. But I have questions for you that when is translation defined? Anyone know? No. Okay, so based on the definition, we have that translation is defined when vector V is defined. Okay? And we can notation is like this. Well, not the translation is T vector B. So we have the translation that transform point M into M prime. And this means vector M prime equals to vector V. Okay? So one more question. In case vector V equals to 0, which transformation is this translation? you know that when vector v equals to vector 0, so point m and point m prime is the same. So we will call this translation is homogeneity. Okay. Okay, so now let's move to the property of translation. There are two main properties of this lesson. The first one, property 1. We have the property 1 like this. If the translation transform m into m prime, and if point m is translated into m prime by vector v, and point n is also translated into m prime by vector v, then vector m prime equals to vector mn. So this property can be easily proved by the vector addition principle. So let's do it together. We need to prove that vector m prime equals to vector mn. So indeed, we have vector mn prime equals to vector v because point m is translated into m prime by vector v, and we also have n prime equals to vector v. Okay, so one more thing is that vector m prime n equals to minus v. So now we have vector mn. Applying vector addition principle, we have vector mn equals to vector n prime plus m prime n. We have vector m prime equals to m prime n plus mn plus n prime. So from this we have vector m prime n equals to minus v, and vector n prime equals to vector v. So v eliminates minus v, so we have only mn left. Okay, so it's proof easily. So in other words, we can say that the translation from this we will translation deserve distance, because vector m prime equals to vector mn, so the length of it also equal. So it's deserved distance. Okay. Let's move to property 2. Property 2. So in property 2 we have some statement like this. A translation maps a line to a line. Yes, it is obvious that if I have a line D here and vector V like this, and we have a translation of D prime like this by vector V. Okay, and next we will have a translation marks a segment to a segment of the same length. This is similarly to a line, but there's one more thing, that it has to be the same length. As we know in the property 1, that translation is a translation distance, so it's also maps a segment to a segment of the same length. Okay, and it maps an angle to an angle of the same measure. And the last thing, the last one is that a translation maps a circle to a circle of the same length, of the same radius, sorry.